Hello everyone, my name is Mohammed Imran and the title of our paper is Distributed Graph Analytics with Datalog Queries in Flink. First we will explain the motivation behind the paper. Nowadays the core requirements amongst others from a framework or system are efficiency, conciseness and ease of use. That means that the system must be able to execute tasks fast, and the user should be able to accomplish the analytics tasks with few lines of code, and the code should be easy to write, easy to maintain, and so on. Therefore, to fulfill these requirements, we implemented Datalog language in Apache Flink. We chose the Datalog language mainly because of its conciseness. Here we show an example of Datalog program's conciseness. On the left side we have an implementation of transitive closure program using Flink and Scala, and on the right side we have the transitive closure algorithm implementation using Datalog. It's clearly visible that on the right side that the program that's implemented using Datalog is more concise than the program that's implemented using Flink and Scala. So with Datalog we implemented the program with only 2 lines of code, whereas by using Scala and Flink we implemented the program with more than 20 lines of code. Hence the Datalog language offers more succinctness compared to other known languages. And the reason we chose Flink is that Flink is an efficient cyclic data flow system that allows for execution of the programs on the distributed cluster of machines. Amongst other APIs and libraries, Flink also provides the dataset API for the batch processing to process the static data set. Furthermore, importantly, Flink provides incremental iterations that are suitable to evaluate iterative programs and Datalog's recursive program. Therefore, we thought it would be suitable to implement Datalog language on Apache Flink with using incremental iterations. Now we will discuss our system, which is called COG, and our system COG is a Datalog evaluation system that offers conciseness through Datalog, and it offers efficiency through incremental iterations of Apache Flink. We made the following contributions in our paper. Our system creates logical plans for the Datalog programs and transform those plans to Flink's dataset based plans, and the Flink job graphs are created from the dataset based plan so that it can be executed on worker nodes. Our system uses the delta iterations of Apache Flink to implement a semi-naive evaluation algorithm to evaluate the recursive queries of Datalog. Finally, we performed benchmark comparison and we experimentally proved that our system outperformed a Spark-based BigDatalog systems in most of the test cases. Now we will have a look at Flink's software stack. At the bottom we have the infrastructures where Flink can be deployed, and the core of Apache Flink is Flink runtime, which is responsible for the execution of programs. It contains some low-level details, and on the top we have dataset API and the data stream API for batch processing and stream processing respectively. Flink also provides JLE, Flink ML and table API for graph processing, machine learning and for relational querying. and Flink implemented SQL as a high-level language on top of the table API, so for it to be used with relational querying. That was before our implementation, and we implemented our system on the top of table API to provide the Datalog support on the top of the relational API to enable users to write programs conveniently and concisely. Now we will discuss the compilation and execution pipeline. First, user writes a program and submits the program to our system. The Datalog parser in our system parses the program and creates the parse tree. The predicate connection graph is then created from the parse tree, which is the PCG is used for querying